All right, welcome back. We're going to be continuing on in section 7.2 in our textbook. This is going to be the difference in sampling proportions. So we want to look at a real life example, Skittles and M&Ms, and hopefully you voted for which is your preference. But we want to see which one has more orange candies, a higher proportion of orange candies. So we're going to take a simple random sample of 50 Skittles and 50 M&Ms and calculate the proportion for each one. And when we do that, my Skittles, I have 13 orange candies out of 50. So my proportion, or p hat, is 0.26. And notice I put a subscript of S to indicate this is a proportion of with Skittles. My M&Ms, I'm calling p hat sub M, just so I can tell them apart. And I only had 9 orange candies in there. So the proportion was 0.18. The difference, and we always wanted to talk about which way we're subtracting them. So I'm going to have Skittles minus my M&M proportion. So 0.26 minus 0.18. So my difference in proportions is 0.08. And we want to create a dot plot now. And so since we're not in class, unfortunately, we are going to use the dot plot that I've created. So here is my scale. And again, remember this represents the difference in proportions of the proportion of Skittles minus the proportion of orange candies and M&Ms. So each dot is the difference between two samples, one Skittles sample and one M&M sample, and the proportion of orange candies in each. And here's what my sampling distribution of p hat minus p hat looks like. And each dot, again, it's important that we remember, each dot is the difference in proportion of orange candies from Skittles and M&Ms. And make a prediction about the shape, center, and variability. Same things we always want to talk about when we're looking at distributions. The shape looks approximately normal. The center looks like it's about at 0.02, maybe between 0 and 0.02. And the variability, I'm guessing at this, maybe 0.06. And I'm kind of getting that by looking from the lowest to the largest and dividing that by 6. Okay, let's take a look now, the next part of this. So we used Google, good old Google now, and found that Skittles supposedly have 21.6% orange candies, whereas M&M's 20% are orange. So we want to describe the sampling distribution of the sample proportion of orange Skittles and the sampling distribution of the sample proportion of orange M&Ms. So two different populations here. So my Skittles, my shape, as long as I meet the large counts criteria, I can call it normal. So I need to check for large counts, and that means when we're dealing with proportions, I take the sample size times the proportion. I got 10.8. It's got to be greater than 10. I then take the sample size times 1 minus the proportion or the success rate. And I, again, have to make sure it's larger than or equal to 10. And it did meet that. For M&Ms, we've got to do the same thing to meet our large sample, our large counts criteria. So 50 times the proportion that are supposed to be in there gives me 10. And it's okay if we equal 10. It can be equal than or greater than to meet the large counts criteria. And I do the same thing with 50 of 1 minus p. And again, that's larger than 10. So both of my populations, I can say, are approximately normal. To find the mean, our mean, so p, is going to be the same as the proportion mean for our sample. So what I'm going to say is that the sample mean is equal to the population mean, which is 0.216 and 0.20 for M&Ms. The standard deviation, the formula that I have for standard deviation when I'm doing a sampling distribution of p hat is p times 1 minus p divided by n, all of that under the square root. And I went through and calculated that for both Skittles and M&Ms for you. And now we want to describe the sampling distribution for the difference between these two proportions. So It's approximately normal because we met the large counts criteria for both of them. The mean of the difference between the two of them, I take the Skittles minus the M&M's proportion. I got 0.016. So again, here's my formula for checking for that. And the standard deviation of the difference between proportions. Now remember, anytime we're looking at the difference between things and we're talking about the variation, we never ever subtract our standard deviations, our variances. So I've got to take the variances for my Skittles, square that, plus the variance for my M&Ms. So that's just the standard deviation squared, and then take the square root of that. So 0.0582 squared, so that's the variance for the standard for Skittles, plus the variance for the M&Ms square rooted, and I get 0.0812. And here's the actual formula. It looks intimidating, but it's not. You just plug in your values there. Now, when we did this, or when this pair of teachers did it, they calculated a difference between the proportions of 0.08. We want to see what is the probability of getting a difference of 0.08 or higher. So we've got to do our z-score. We can say it's approximately normal from here because it met the large counts criteria. We've calculated our mean and our standard deviation. I've drawn my normal curve with my mean. The value I'm looking for is 0.08, and I want R higher, so I'm shading to the right. To find the z-score, so I look at the value I'm looking at, the observed value, 0.08, minus the mean divided by the standard deviation. And I come up with a value of 0.79. Now, because I want greater than that, I've got to go to my table, and I find the value of 0.7852, but I've got to subtract that from 1 to get the greater than. And 1 minus 0.752 is 0.2148. So that is the probability of getting a difference between my Skittles proportion and my M&M's proportion of 0.08 or greater. And here's what the actual z-score we're putting in, how we're getting all these numbers. And again, this is why I don't like you to see the formula to start with, because it looks so intimidating. But it's just p hat minus p hat from the second sample. So that was my Skittles sample minus my M&M sample. And I'm going to subtract the population proportion of my Skittles population minus my M&M's population proportion. And then we're plugging in all the values down here. And again, they're pretty straightforward when we're plugging them in. Okay, and let's take a look at the last part here, summarize our notes. Oops, sorry, I thought I had that separated already for us. And it looks like there's a lot here. So 2 learning targets. When we're dealing with a sampling distribution of p hat 1 minus p hat 2. So a sampling distribution of the difference of 2 proportions. The shape is going to be approximately normal if we meet the large counts criteria. And the large counts criteria is that the sample size from the first population, or sample size, from your first group, times the probability in the first group has to be greater than 10, and the sample size times 1 minus the probability has to be greater than or equal to 10. And you do the same thing in your second population and sample. So the sample size of your second group times the probability of the second group has to be greater than or equal to 10. And same thing, sample size of multiplied by 1 minus your probability of the second population. The center, we just simply subtract the 2 probabilities. So to find the center for our difference of 2 proportions, we take the proportion of the first one minus the proportion of the second of the populations. Our variability for the difference of 2 proportions is this long formula, which is the square root of the probability of proportion from your first population times 1 minus that probability divided by the sample size of your first population, that you take from your first population, plus, make sure you remember that's a plus, the probability in the second population times 1 minus that probability divided by the sample size that you take from the second population. And our normal calculations is our second learning target. Again, there's our mean, and here's my standard deviation. So I'm going to be using those up here. And in the center is the difference between the two proportions of our population and then the observed one. So what are we looking for? So the difference between those two observed ones in the sample minus the difference in the proportions from the population divided by the standard deviation. And then you would go to your table to find that. Okay, again, for the check your understanding, highly encourage you to try this yourself first before looking at the answers. And the answer key is online. If you have questions about how we got any of those answers, please let me know, and I'd be happy to go through them with you. Okay, on to the homework for section 7.2.